Hi, in this video we are going to look into another lecture in the series of operating system academics or academic series of operating system. So boys and girls, so far we have seen introduction to operating system and the background, and then thereafter we started with various modules of process management, like we did process concepts and multi-threading or threads, and subsequently we have also seen CPU scheduling, series of 5 lectures in CPU scheduling covering all the scheduling algorithms which are primarily used in a multi-programmed operating system environment. So another module or another component of process manager or process management is a very important module which is generally called process synchronization. So boys and girls, this is lecture number 10 in this series, and we are going to begin our discussion with process synchronization in this model or in this module. Okay, so synchronization is also known as process coordination. Okay, we need to essentially understand what exactly is the meaning of synchronization and what exactly is the need for synchronization. Why do we need synchronization? And having understood what is synchronization, why do we need synchronization, addressing the question of what and why, we have to basically look into how to achieve synchronization. So you can see, let me start. So as usual, the disclaimer that this content that we are delivering here is essentially from the instructor resources of the Galvin textbook, Operating System Concept 10th edition. Okay, that's the content. So topic name is process synchronization, chapter number 6, essentially in the textbook of operating system. As I mentioned, it is also called process coordination. So before we start understanding what exactly is synchronization, why synchronization is needed, we need to first understand what is called IPC. Okay, so let's before I come to this point, I would make a generic definition or general discussion on the IPC concept, because synchronization essentially implies the presence of IPC. If there is no IPC, there is no meaning of synchronization. So even though IPC is a broad topic, a major topic, but from the academic perspective and also the GATE exam and other competitive exams perspective, you don't have to go deep into the concepts of IPC. Essentially, a brief background is needed, which I'm going to provide here. So boys and girls, IPC stands for inter-process communication. You may say inter-process or you may say inter-thread also, there is no problem. Inter-process communication. So what exactly is IPC and how do we achieve it, that we will see. So first of all, I would say that generally if there are two entities in this universe or in this world, if there are two entities, I will call this as entity 1 and entity 2. These entities can be like human beings, or these entities can be two computers or any digital equipments or digital components. And if they wish to communicate with each other, like two computers wish to communicate with each other, or two cell phones, if they wish to communicate with each other, two human beings wish to communicate with each other, then what is the basic requirement of communication? How is this communication done? So as you know, for ensuring communication between between these two entities in this universe, you require a shared media. The medium which is shareable to both the entities, shared medium is needed. Like in the context of computer communication, the media could be classified as hardware and software. The hardware essentially consists of cables, connectors, network interface card, and the software media includes the communication protocols like TCP/IP. Human communication also need media in the form of air carrying the electromagnetic media, and the voice, and that is the voice being carried by the electromagnetic media, and the software media is the language. Similarly, for any two entities, we follow this model of medium. Without medium, communication is not possible. Same way, if these two entities are in the context of operating system as processes, imagine for example, this is process 1 and process 2. So if they wish to communicate with each other, they also need a shared media. And these mediums has to be outside the address space of the processes. It cannot be within the address space. People sometimes think that global variables can be used, but global variable, if I define in process 1, it will only be confined to that process 1. It cannot be accessed beyond or outside process 1. So I cannot use global variables for ensuring communication between two processes. I need some separate shared media. And this medium, which is being supported by operating system, which is being provided by the operating system, is called IPC mechanism. Mechanism that allows, the medium that allows the processes to communicate are called IPC mechanisms. The important characteristic of this mechanism is that it will be shareable to both, it will be accessible to both the processes, supported by, right, by control, providing the control by operating system. Means to create this media, manage this media, we have to use system calls, like for example, to manage or create that media and use as a medium for ensuring communication, I will have to use like system calls. Like popular, what are the popular media? I'm going to show you shortly after some time. What are names of these medias which are generally supported in practical operating systems like Unix, Linux and Windows. So that is the essence of communication. In order for ensuring communication, there must be some shared media. Media could be in the form of several entities. I already told, right? What could be the possible entities for, what will be the possible media for ensuring communication? So as far as entities or processes, this media is supported and provided as an important resource by the operating system, which is called IPC mechanisms. And discussion about the IPC mechanisms involve doing some programming, which is beyond the scope of this subject or this class curriculum. You don't have to prepare for IPC mechanisms in practice through Unix or Linux or Windows. You don't have to really do that. Okay, that is purely specific to the corresponding operating system. What is the essence that we need to understand here is, in order for processes to communicate, I need some shared media, without which communication is not possible. Okay, like here we will have some points with regard to IPCs. Processes within a system may be classified in the context of communication as either independent or cooperating. Independent means they are not communicating, there is no shared resource, that's the meaning. There is no communication going on between the processes. Otherwise, if there is some shared resources and processes are communicating, essentially in the literature they are called cooperating, and the other word for cooperating you can say communicating. We can even say communicating processes. So processes are categorized into two types, independent and communicating. So communication implies the presence of shared media. Mechanism whereby one process can communicate or exchange data with the other process. IPC is a mechanism where it allows processes to communicate via exchanging the data. A set of techniques for the exchange of data among multiple threads, multiple processes in one or more processes. That is IPC. So processes may be running on one processor or one computer, or maybe different computers connected in a network. So it can be a single computer-based communication, or it can be a network-based communication. So processes within a system may be independent or cooperating, and cooperating or communicating processes can affect or be affected by the process. I will talk about that later. Now, essentially, why should they communicate? What are the basic reasons for the processes to communicate? One essential reason is resource sharing, communication, exchanging the data, sharing the resources. And exchanging the data, dividing the work into modules and exchanging it, sharing it across different processes will make the computation faster, computational speed up. It will allow you to have a modular design of the software, and it will provide ease or convenience of communication or convenience of sharing the data. And communicating processes need IPC mechanisms. That's I have been always emphasizing. And generally, by and large, in most of the operating system, there are two models which are followed for IPC, two models of IPC. One is called shared memory model and the other is called message passing model. So any IPC mechanism, boys and girls, any IPC mechanism supported by the operating system will have to be in the either supported by the model of shared memory or through message passing. So how do shared memory model look like? Look at the diagram. This is a shared memory model. Here I have two processes. Have a closer look at this diagram, boys and girls. Have a closer look at this. This is process A and this is process B. And outside the processes, I have this shared memory block. A segment of memory which is called shared memory, is present between the processes through which they communicate with each other. Look at this. They are communicating through the shared memory model. The other approach is you are going to create a sort of global queue, for example, which can be used by the processes to communicate. You send the messages in the queue. The queue may follow some order like FIFO order, LIFO order, and then you can ensure communication between them. So any of the IPC mechanism like pipes, message queues, FIFO models, or shared memory segments will either come in the model of shared memory or message passing. This point we have to conceptualize. Like this is a conceptual view of an IPC through a mechanism by name pipe. So pipe is an IPC mechanism which belongs to the model of a queue. Pipe is just like a logical file created between two processes, which has like file descriptors. We have pipe descriptors, pipe descriptor 0, pipe descriptor 1, indicating the read end at the right end of the pipe. So this pipe is a media between these two processes through which they can send and receive the messages. They can send and receive the messages. So this process can write through this identifier, and this process could read from this identifier. So this may belong to, like, you can say, message passing system. Okay. So just to give you an overview, like in what are the different versions of Unix IPC mechanisms, like Unix and Linux IPC mechanisms falls in the category of pipes, message queues, semaphores, shared memory, sockets, and RPC. RPC stands for remote procedure call. Sockets and RPC is basically for network-based communication, and the remaining can be for network or can be for independent machines. So these are some of the IPC mechanisms which are supported by Unix and Linux environments. So boys and girls, the nutshell, the summarized discussion is that any multi-programmed operating system will provide some IPC mechanisms using which the processes can communicate through each other or communicate with each other. Now the questions, please, as far as IPC background is concerned, this is sufficient enough to gear up ourselves to understand the meaning of synchronization. So now time comes to define what is synchronization. In my own terms, I generally used to say that synchronization is an aftermath of communication. Say aftermath. That means if there is no communication, there is no meaning of synchronization. Hereafter, we'll write synchronization in short as sync. All right, just we'll write in short as sync. Any communication should be in sync. Communicating entities should be synchronized. Synchronization is like a particular protocol to be followed by the communicating entities to ensure a proper coordinated communication. If the communication entities are not in sync with each other, are not synchronized with each other, then essentially it will create or it will lead to problems. Okay, so synchronization is like a protocol to be followed by both the processes for an orderly delivery of data, orderly exchange of data between them, so that there is no, as such, any kind of problems arising, okay, in that IPC environment. So once again, I am emphasizing, just like we say that there is no concept of process without a program. I can't create a process without a program. Similarly, there is no concept of synchronization without IPC. So if I have an IPC environment means what? I have processes and shared media communicating with each other. Then comes the matter of synchronization. We say that IPC model should be in sync. If there is no IPC, there is no meaning of synchronization. I can't have synchronization alone, just like I can't have a process without a program. I can't have a thread without a process. Is it not? Just like that. So if I don't have the IPC environment in sync, if the processes communicating with each other are not in sync, then what essentially are the problems that are going to arise? What problems are going to arise? Lack of synchronization, lack of coordination may potentially lead to what kind of problems? These kind of problems are similar to like human communication. I generally used to say, for example, when a physical class is going on between the faculty and students in a lecture room, that is also a communication environment. So don't you agree that the students, right, learners, should be in sync with the educator? Yes, of course. The students should be in sync with the faculty and the faculty should be in sync with the students. Otherwise, it may lead to problems. Like people may say that if the faculty and the student, they are not coordinated, then you may say the students would go and complain to their dean or HOD or principal saying that we are unable to follow. Right? Whatever teacher is saying, teaching, we are unable to follow. The reason for not following could be anything. Maybe the language problem, or maybe the flow of the teacher, or whatever it is. Okay, so that may lead to a problem. Or maybe sometimes it happens that whatever teacher is trying to tell, students are not properly grasping it or misunderstanding it. So that is nothing but the first problem, which may happen in a process environment also, which we generally call it as inconsistency. Inconsistency can arise. The communication should be consistent. That is what we are trying to say. If there is no proper synchronization between processes, then it could lead to inconsistency. Inconsistency, it also implies incorrectness, wrong results. We may get wrong results. Incorrectness. If not inconsistency, sometimes the communication may lead to data loss when there is no proper synchronization. Like particularly this concept can well be understood if you take an analogy of a network communication. Sender and receiver should be in sync. Like if I have a faster sender and slow receiver, what problem are we going to face? As you know very well, in the context of networks, you call that as flow control, fast sender and slow receiver. Fast sender will pump the data at a faster rate which the receiver cannot handle. And in that case, what will happen? You will lose the packets, you will lose the data loss will happen. So same way, in a communicating environment also, IPC environment as well, we can face the same situation. Data loss may happen. If not the data loss, sometimes even particularly in IPC environments, we can face a situation of undesirable situation of what is called deadlock. And in network communication, generally this is also called lockup, which is also an undesirable feature. All these things, all these features, as you see, boys and girls, as you see here, is undesirable. We never want inconsistency, we never want data loss, we never want deadlock. So if somebody questions what is the need for synchronization, why synchronization is needed in an IPC environment, simply you can say to make sure that we require we require synchronization in IPC environment, or we want IPC environment to be in sync to make sure that there is no inconsistency, data loss, or happening of lockups and deadlocks. That is the answer of why. Like to give more concrete examples of synchronization, to build up understanding of what exactly is synchronization, I used to give several real life examples. Like imagine, for example, there is a popular example which you find in many textbooks. There are two houses, house 1 and house 2, two apartments or two houses. And in between the two houses, let's imagine, for example, there is a small lawn, LAWN lawn, right? Which has a grass and some small garden type in between the two houses. And this is shareable to both the houses, both the apartments. Suppose, for example, if this house owner has some pet cat and this house owner has pet dog, then can they release their pets into the lawn without a protocol, without an understanding? No. If they do so, you may face problems. I don't have to illustrate or elaborate what kind of problems you are going to face. So invariably, these two are like communicating entities, these are shared media. They need to have some order, they need to have some discussion among them, and that is what is synchronization. They would have to basically make a discussion saying that, like this house owner will say, sir, I will use morning session, will you use evening session for your pet to graze or maybe come out onto the lawn? Then if they agree, there will never be a problem. If they don't agree, then there will be a problem. So therefore, a proper synchronization is needed between both these owners. Okay. Amazon purchase or any commercial e-commerce applications, banking, net banking, right? Reservation systems. These are all examples of synchronization, an environment where synchronization is needed. Like for example, you take the case of reservation, airline reservation. You are reserving, you are trying to reserve a seat going from one place to another place, going to Delhi, let us say. I reserve a seat. There is only one seat available, free seat available. The software at the back end, at the server side, has to be in sync with the client side software. If there is no proper synchronization, it would lead to chaos. Suppose, for example, if the software at the server side of the flight, right, whichever flight, suppose if it is not in sync with the client, suppose it takes the amount and gives the seat to all the customers. There are 5 customers trying to reserve the seat together at the same time. Maybe airline, maybe train, maybe bus. So if the software basically erroneously take the amount from all the 5 customers and allocate the seat to all because of lack of synchronization, then what is going to happen on the day of flight, on the day of train? You imagine everybody would come and say, this is my seat, and that is what I mean by inconsistency. Same way accounts, shareable accounts, multi-customer accounts. An account is being held by multiple account holders. One person residing in Delhi, one person residing in Bangalore, another person residing in Chennai, and all 3 on their account they are trying to basically credit or debit. One person is trying to debit the account, the other person is trying to credit the amount. If the software is not in sync, then it would lead to problem. So those are the examples. Amazon purchase, there is only one item available. Different customers are trying to purchase it. And if the software is not in sync, then essentially the company side software, server side software may correct the amount from everybody and may have to deliver only to one person. Then others will lose their amount. So these are all simple examples that emphasize the requirement of synchronization in IPC environment. Any communication environment should be in sync. Lack of synchronization invariably may lead to potentially some problems. So in this regard, generally we say that the type of synchronization, if you classify type of synchronization, type of processes in IPC environment to be in sync, that's what we call type of synchronization. So if you talk about type of synchronization generally involved in IPC environment, we say that there are 2 types. The processes may belong to 2 categories in this type of environment. One is called competition, where processes are competing for accessibility of shared resource, and the other is called cooperation. Now generally this classification is there in the not operating system textbook, but it is there in the programming principles where you talk about concurrency. There you find this classification. Competition and cooperation. Competition means 2 or more processes are said to be in competing environment if and only if they compete or contend, CONTEND, contend for the accessibility of a shared resource. Like for example, a simple example of competition. I have 2 processes, process P1, process P2, and they are accessing a shared variable. This variable C, this process P1, this process P2. So process P1 want to make an update and process P2 also wish to make an update. This process want to increment the value by 1, this process want to decrement the value by 1. Presently the current value is 6. This is what is the scenario or situation at time t. P1 wish to increment it by 1, P2 wish to decrement it by 1. So after both the processes finish their update in any order, whichever order, P1 first, P2, or P2 first, then P1, the final consistent value should be 6. But if I don't get, if I get other than 6, that is what I call inconsistency. So examples which I quoted like net banking, e-commerce applications, commercial purchases, Amazon purchase, etc., they all belong to this model, competition. Cooperation means invariably the processes should get affected by each other. Cooperation. Processes gets affected by each other. The execution of one process will affect the execution of other process. Execution of one process will affect the execution of other process. The classroom example environment which I gave belongs to cooperation type, like teacher and students. If students make a hell lot of noise, the faculty will get affected. If when due to the teaching, due to the knowledge of the teacher, the students' knowledge will get affected. That is cooperation. And the best possible example generally we find in the literature with regard to cooperation is a well-known problem called producer-consumer. As you know very well, producer-consumer are 2 processes. They are accessing a shared resource. They are accessing a shared variable, right? Or shared buffer, shared file. One process is trying to enter items into the buffer, the other process is trying to consume the items from the buffer, right? Producer and consumer. So they are getting affected by each other. When the buffer is full, producer gets affected by consumer. When the buffer is empty, consumer gets affected by producer. So producer consumer in that regard are said to be cooperating with each other. Generally, by and large, it is an observation that in a competitive environment, boys and girls, please remember, in a competitive environment, when the processes are not in sync or coordination with each other, it may lead to inconsistency or data loss. And when there is a cooperation going on between processes, and if they are not in sync, it may potentially lead to deadlocks or lockups. Okay, so that's the general scenario. So this is the concept. You can see here an example for illustration of competition leading to inconsistency. Like there are two processes, P0 and P1. They are creating child processes using the fork system call. So a typical race condition can exist. The act where processes are contending to access the shared resource is what is termed as race condition in the literature. So race condition means the situation where multiple processes are trying to contend or update or access a variable, and the final outcome depends on the order in which they finish their update. The final value may be 6 or maybe 5 or maybe 4. It depends on in what order the processes are updating the value. Like here, there is a competition going on between the processes when you are creating a child process through a fork mechanism. Like both the processes are calling fork. So as you know, fork system call is going to return the value of the child ID. It is going to assign a new process ID to the child. So invariably, it means that in the kernel, in the operating system kernel, we are maintaining a global variable by name next available PID. It's like a counter, next available PID, which is going to return a new process ID to every created child. So here in a typical concurrent environment, what is happening is P0 and P1 both have simultaneously concurrently called fork. So they try to access, that means the fork routine tries to access next available process ID variable, value of that variable as a next ID for their child process. Suppose imagine it right now that value is 2615. If there is no proper coordination existing here in the operating system kernel, there is a possibility that the same value may be returned to both the processes, and that is totally absurd. That is totally dangerous, because I can't have two processes with the same ID. This child will have the same ID 2615. This child will also have 2615, which will lead to chaos, and that is what we are saying, race condition leading to inconsistency. So this child will also, the child created by P0 will have ID 2615. The child created by P1 will also have ID 2615. This is what is considered as competition between them, leading to a situation like inconsistency. I got wrong results. I can't have two childs with the same ID, and that is what is the race conditions, right? So race condition on kernel variable next variable ID, which represent the next available process ID, right? Unless there is some mechanism to prevent, look at this, unless there is a mechanism to prevent P0 and P1 from accessing the variable next available ID, the same PID could be assigned on two different processes, and this is what is a very clear example of inconsistency, and we never want this type of inconsistency. Okay? So based on this, we basically try to say that in an IPC environment, if I have set of processes, okay, and if there is a race condition going on between the processes, there is a race going on between the processes to access the shared variables like next available ID or variable C or shared resources, right? And if the environment is preemptive environment, that happens, the race will lead to problem only when the environment is preemptive environment existing. Then if these three conditions exist, that means set of processes accessing shared resources, shared resource. So therefore I will mark like this, accessing shared resource, and there is a race going on between the process, and assume the preemption existing. So in the circumstances of these three conditions existing, there is every liability possibility that I may encounter a problem. We may have inconsistency, we may have data loss, we may have a deadlock arising among the processes. So if you don't want any problem to arise, then I need to have a sort of mechanism, a protocol that is going to govern among the processes so that they have a proper coordinated access on the shared resource. So therefore, essentially, a sort of protocol is needed, right? That protocol becomes the solution to my problem. So in the literature, solving this problem, this particular problem is given a name as what is called as critical section problem. Okay. Critical section problem. Every problem will have a name. The name which is given here is called critical section. So this presence of shared resource implies critical section. I will write critical section in short as CS. We will write critical section in short as CS. So that means in any IPC environment, if there are critical resources, if there are critical section, okay, in any IPC environment, when there are critical sections, critical resources, shared resources, if there is a race going on between processes and if the environment is preemptive environment, there is every potential possibility that we may encounter a problem. So if you don't want a problem, I need a solution. So name of that problem is called critical section. The name of the problem itself is given as critical section problem, and the solution for the algorithm for this problem, the solution or the algorithm for this problem is what is termed as synchronization mechanism. Synchronization mechanism. So this is the terminology. So how is that model? How is the architecture of that synchronization mechanism? What is it made up of? That we have to see, and how are these synchronization mechanisms categorized, and chronology, etc. we need to understand. So let's see this. This is the framework, you can say, for critical section problem. So every process participating in IPC environment will have critical section. Just now we defined. Let me underline this. Will have critical section. It is nothing but piece of codes, critical section, a segment of code. Processes may be changing common variables, updating table. That is critical section. Examples of critical section in operating system context may be common variables, updating table, writing to file. So when one process is in critical section, nobody else should be allowed to access. Otherwise, we will face the problem of inconsistency and others. So name of the problem, I said just now, the name of the problem is critical section problem. Is to design protocol which will solve my problem to ensure there is no inconsistency, data loss or deadlock. So each process must ask permission to enter critical section. So what is the architecture? I said, what is the model of that solution for synchronization mechanism? The synchronization mechanism will have a solution which will have three parts. One is called entry section. Please understand. We'll have three parts. One is called entry section, right? The other is exit section, and the other part, last part, is called remainder section. So if you want me to show it pictorially, it will look something like this. It will look something like this, right? So, or maybe another diagram is there. Let me check. Okay. So in another diagrammatic form, we can show it something like this. Then I will talk about it. The generic way or abstract view of the synchronization mechanism I will exhibit here. So this is entry section, and imagine this is critical section, and this is exit section. Okay, so this is critical section, this is entry, and this is exit. This is model. You can say this is a model or architecture, okay, of synchronization mechanism. Solution for my critical section problem, synchronization mechanism. So when multiple processes may be contending to access critical section, P1, P2, so on, P3, and so on. Any number of processes are contending to access critical section. The job of this entry section is to allow only one process to gain access of critical section. And when the process come out from critical section, will execute the exit section part to intimate that critical section is over. So this part of exit section here, invariably I would say, is to intimate, notify. This will send the notification signal that critical section has become free. And let me tell you that together this entry and exit define what is called synchronization mechanism. So every model will follow this architecture. Every synchronization mechanism will follow this order, this model, this architecture. Okay. I can have, let me tell you that remainder section may be here or maybe here also before the processes. Remainder section can be anywhere. Remainder means non-critical section, remainder section. So this can be remainder section. Non-critical section code of the process is called non-remainder section or non-critical section. So this is the view of this. So you can check here. I have entry section, critical section, exit section, remainder section. So boys and girls, this is what is called the general structure of a process PI participating in an environment having a mechanism called synchronization mechanism to make sure a well coordinated communication environment between the processes. Okay. Consequent to this, the most important topic that we need to discuss is whenever the environment is communicating environment, and when we want to develop a solution for it, when I have some problem, critical section problem, I have synchronization mechanism. When can I ratify that my synchronization mechanism is correct? We generally say that the algorithm is said to be correct if it satisfies all the requirements of the problem, right? If it satisfies all the requirements of the problem, then only I say the solution is correct. So this critical section problem, the solution is synchronization mechanism. So what are the requirements of critical section problem which has to be fulfilled by the synchronization mechanism to classify it as the correct mechanism? So there are three requirements, boys and girls. So let me write it here. Requirements of critical section problem to be fulfilled by synchronization mechanism to classify as the correct mechanism. What are requirements? So as you know very well, you might have studied in the literature, there are three requirements. Number one, mutual exclusion. Number two, progress. Number three, bounded weight. So if any synchronization mechanism that you develop, if it guarantee or satisfy these three requirements, mutual exclusion, progress and bounded weight, then we say the solution is correct. By saying solution is correct, by saying synchronization mechanism is correct, invariably you are endorsing that my environment will never have any problems of synchronization like inconsistency, data loss or deadlock. That is a big. So therefore it will take some time to understand what exactly is mutual exclusion, progress and bounded weighting. So in the next lecture we'll start our discussion with requirements of critical section problem by way of developing understanding what exactly is mutual exclusion, progress, bounded weight, and then we'll see the classification of mechanisms, and then one by one we'll take up and understand different synchronization mechanisms. Okay. So as of now for this lecture, up to here we will stop and we continue with the requirements in the next lecture. Take care. Thank you.